Okay, so now we are changing place. We are moving in Baja California, in the Gulf of California, and I'm presenting a study of fission track study. The Gulf, first, a short introduction about the Gulf. The Gulf of California is a youthful high oblique rifting, and it represents the boundary between the Baja California microplate and mainland Mexico, which belong to the North American plate. Due to the high obliquity of the rifting is characterized by long segment of thrust of fold interrupted by short spreading center. To explain the time-space evolution of the rifting, in the literature, three main models have been proposed. The first two models agree in that the rifting initiated after the end of the subduction of the Guadalupe and Magdalena microplate of Western Baja California. But apart from this, the first model envisage a two-stage models in which there will be a phase of orthogonal rifting or protogulf, followed by dextral transsectional shearing within the Gulf, initiating at 6.5 million years. The second model, that is called one-stage model, envisage a right lateral oblique rifting within the Gulf since the end of the subduction. Then there is a third model that is called a three-stage rifting model, that envisage a start, an onset of the extensional deformation in the region of the Gulf much earlier, in late Oligocene, early Miocene. And there will be a stage of wide rifting in which extensional deformation affect a large region comprising the Sierra Madre del the Eastern Baja California, and then there will be a focusing of the extensional deformation in the place of the proto-rift, and then starting with the end of the subduction, there will be the development of the transsectional deformation. To investigate about this different model, we have performed a fission track study across the Gulf with sample collected in the eastern part of Baja California, on the islands, inside the Gulf, and on mainland Mexico. The sampling has targeted the Cretaceous batholites outcropping in Baja California and inside the Gulf, and also the early and middle Miocene plutons exposed in southern Gulf of California and inland Mexico. Most of the sample have been already dated with uranium lead and argon-argon methods. So this is people speaking before me have already explained these figures, but what thermochronology can tell us about rifting. First of all, because of the cooling of the football rocks along normal faults, what we can do is to date normal faults in rifting, and so to give the time of the rifting. And this is only happened if the magnitude of the throw along the fault is sufficient to bring to close to the surface rock that before the movement along the fault were completely reset. So the thermochronometer start to record again an age due to the movement along the fault. The other way in which thermochronological method can use to investigate about the rifting has been shown by Said before, according to the pattern of the ages across the margin. So I've already said that samples were already dated with uranium lead and argon-argon on various minerals. And here is to show you a little bit about the difference between geochronometers, high temperature thermochronometers, and low temperature thermochronometers. In fact, here we can see various cases that we have encountered during the study. We have a case A in which we see that the uranium lead, so the geochronometer and the high temperature thermochronometers give an age that overlaps. So in this moment, for this sample, geochronometers and high temperature thermochronometers are just giving the age of the emplacement of the plutonic rock. But we see that the low temperature thermochronometers, the fission track, are giving a much younger ages, about 9 million years. So they are giving, so fission track is giving information on the post-emplacement history. And in particular, in our case, as we are dating footwall blocks, we interpret these 10 million years as the age along of the movement of the fault. So we are dating the fault. In the second sample that we have brought as an example, we have a case B in which we see that high temperature thermochronometers and low temperature thermochronometers overlap. They are giving the same age. So what this can mean just simply that the Pluton emplaced at a level that is very shallow. So we are just dating with all this method a magmatic cooling, or is possible that we are still dating a fault, and we have a Pluton that is in place in the locus of the fault, and then is immediately brought toward the surface. Then we have a case C in which we see a Cretaceous batholith, and we see this plot on a side. What we have obtained? We have obtained a fission track ages giving an intermediate age of 25, but the age distribution is not passing the chi-square test, and the chi-square test is telling us that the age distribution is composed by different components. In this case, we can deconvolve the ages, and we obtain two ages: an old ages of 65 million years that is likely due to magmatic cooling, the cooling after the emplacement, and the very young ages that is almost 7, that is a minimum ages. Usually this minimum ages is interpreted as recording the last cooling of the rocks. The last cooling of rocks below a temperature, because it's in practice, it's a population of apatites that are very sensitive to temperature, and so very present a cooling below around 60 degrees. And so even in this case, in this more complex case, likely we are dating really the movement along the fault plane. To interpret all this variability of cases, we have plotted the data according to their distance from an imaginary line that is placed upon the rim of the escarpment of the high elevated rifted margin of the Baja California. And we can see that we have this kind of trend. We have onshore Baja California a group of ages with a certain spreading that goes from old ages around 70 million years to 17. Then moving towards east, we have a sudden drops of the ages, and we have the youngest ages that we have obtained around 6 million years. Then these ages are growing up again, and they reach values of 10, 12 million years going towards mainland Mexico, and these ages are found also in mainland Mexico. Then another thing that I want to that you point the observation on is the fact that on Baja California onshore we have a cluster that is this here circled, a cluster of early Miocene ages between 10 and 70 million, or between 20 and 70 million years. These ages are in part from the studies and in part from a study from Mark et al. 2014. And how we can interpret this age. In the paper of Mark et al., they are interpreted as a local thermal event affecting samples coming from the Cretaceous batholith. But in our interpretation, this could be a more, as we have found ages of this type, this could be a much larger regional thermal process affecting the margin that could be linked to the wide rifting stage envisaged by the third model of the evolution of the rift, and or in some cases, it could even be a movement along default representing the old basin of the wide rifting stage. Then, going further east, we have the Pescadero Basin, in which there is still today the boundary between the two plates, and we have that on both the shared margin, we have ages of 12, 10 million years. So we can interpret these ages as this pull apart oceanic basin has been evolved from a translational basin starting really at the end of the subduction around 12, 10 million years. And then another peculiar thing that we have found is that we have the youngest stages are not located in the Pescadero Basin, but they are located in a belt that is close to the Baja California coast. It is around 6 million years. And how we can explain this belt? It is probably that today part of the transtensional deformation is localized, is moved toward west, close to the margin. And so part of the extensional deformation is accommodated along this belt. And this also testified by the presence of recent earthquake showing an extensional signature.
Okay, now we're at 12 minutes now.
Yeah, okay, but I finished. Sorry, I was too...
Timing. That leaves us some time for questions. If you have some, raise your hands, and thanks for the talk. Well, while people think about questions, I have one right to these aspects that you mean there. How can you think of this, that you have migration of deformation away from the mid-ocean ridge, where the mid-ocean ridge should be the weakest area that we have?
Yes, okay.
Why would there any stress be left for these kind of deformation?
No, it's not. First of all, okay, the crust has been thinned a lot during the localization of the stress after the white rifting stage. So probably, and also this is because we have the Pescadero Basin, but then we have to the west the Alarcon Basin, the Farallon Basin. So in practice, this, how to say, but this trend is intercepting other small spreading center in which the stress is localized. So probably it's because this belt intercept other spreading center located in this area. So, and then all the crust has been thinned before. So, and then there is, anyway, there is the evidence of the earthquake placed in this area. And also some extensional fault of that age have been found also in close to this area in the south of Baja California. Los Cabos and things like this. So we think there is a movement in that sense.
Okay, thanks. Joanne, you have a question?
Yes. Can you hear me okay?
Yep.
Yeah.
Okay, so this picture that you're showing us on the right now has a bunch of red dots that look like they're in the water, like 13.0.
Yes,
I wondered where it actually is, because it's obviously not really where it's plotted.
Yes, I'm sorry, I forgot to tell this, but this sample comes from also from blocks, submerged blocks. This is part of a study of Duque Trujillo that was performing uranium lead and argon-argon datings, and they are drilled in the submerged area of the Gulf. That's why you can see all the variation.
Okay, but that one that's 13 million years. It's like in the part that's a new crust, isn't it? According to your map.
Sorry, I cannot see, but.
Oh, okay. It's just the last figure that you showed us.
Yeah,
this one with the earthquake focal mechanisms. Yeah.
Okay.
So if you look at the central earthquake focal mechanism and you look south of it, there's an 8.1 and then there's a 13.0 million years.
Okay,
but that
here,
13.0 is like inside the younger oceanic crust. So maybe the block was, I don't know where the block couldn't have been in place.
I don't know.
Because the oceanic crust there is only less than 6 million years old.
Okay, these are plutonic rock, are early Miocene and early Miocene and middle Miocene plutonic rock. They have been studied, so is I mean they are not belonging to the oceanic crust.
Okay, so maybe it's just not quite in the right spot. Okay, thank you.
Yeah.
And one last question from Valerie.
Yeah, so I'll just go, with a quick one. Do you have any comments on the orientation of the focal mechanism nodal planes relative to the extension direction? Because I guess the extension direction here, I mean, sigma 3 is a little bit of northwest-southeast, but the focal mechanisms show not northwest trending nodal planes, and it looks like pure normal faulting. I don't know if you have any comments on that.
Not more particularly.
Okay.
I'm sorry, I'm a thermochronologist.
No problem, I figured. Thank you.
They were preparing the figure, but they told me that they thought that it's extensional. They are extensional focal mechanism.
Right.
It's probably
right.
Okay.
All right. Thank you.
I find that very interesting. It seems to be some kind of strain partitioning, so rotating fields perpendicular to the coastline or to the stretching direction.
Right.